Projective Geometry, Volume 1, by Oswald, Veblen, and John Wesley Young.
Chapter 9, Geometric Constructions, Invariants. Section 86, Problems of the Second Degree. We have seen in Section 83 that any problem of the first degree can be solved completely by means of linear constructions, but that a problem of degree higher than the first cannot be solved by linear constructions alone. In regard to problems of the second degree in a plane, however, it was seen in Section 84 that any such problem may be reduced to the problem of finding the points of intersection of an arbitrary line in the plane with a particular conic in the plane. This result we may state in the following form. Theorem 5. Any problem of the second degree in a plane may be solved by linear constructions if the intersections of every line in the plane with a single conic in this plane are assumed known. Assumptions A, E, P, H0, K2. In the usual representation of the projective geometry of a real plane by means of points, lines, etc., drawn with a pencil, say, on a sheet of paper, the linear constructions, as has already been noted, are those that can be performed with the use of a straight edge alone. It will be shown later that any conic in the real geometry is equivalent projectively to a circle. The instrument usually employed to draw circles is a compass. It is then clear that in this representation, any problem of the second degree can be solved by means of a straight edge and compass alone. The theorem just stated, however, shows that if a single circle is drawn once for all in the plane, the straight edge alone suffices for the solution of any problem of the second degree in this plane. The discussion immediately following serves to indicate briefly how this may be accomplished. We proceed to show how this theorem may be used in the solution of problems of the second degree. Any such problem may be reduced more or less readily to the first of the following. Problem 1. To find the double points of a projectivity on a line of which three pairs of homologous points are given. We may assume that given pairs of homologous points all consist of distinct points, otherwise the problem is linear. In accordance with Theorem 5, we suppose given a conic in a plane with the line, and assume known the intersections of any line in the plane of this conic. Let O be any point of the given conic, and with O as center, project the given pairs of homologous points on the conic. Figure 98. These define a projectivity on the conic. Construct the axis of this projectivity and let it meet the conic in the points P, Q. The lines OP, OQ then meet the given line in the required double points. Problem 2. To find the point of intersection of a given line with a conic of which 5 points are given. Let A, B, C, D, E be the given points of the conic. The conic is then defined by the projectivity D parentheses A, B, C, projective with E parentheses A, B, C, between the pencils of lines at D and E. This projectivity gives rise to a projectivity on a given line of which three pairs of homologous points are known. The double points of the latter projectivity are the points of intersection of the line with the conic. The problem is thus reduced to Problem 1. Problem 3. We have seen that it is possible for two triangles in a plane to be perspective from four different centers, chiefly Exercise 8, page 105. The maximum number of ways in which it is conceivable that two triangles may be perspective is clearly equal to the number of permutations of three things, three at a time, i.e. 6. The question then arises, is it possible to construct two triangles that are perspective from 6 different centers? Let the two triangles be A, B, C, and A', B', C', and let x sub 1 equals 0, x sub 2 equals 0, x sub 3 equals 0 be the sides of the first opposite to A, B, C, respectively. Let the sides of the second opposite to A', B', C', respectively be x sub 1 plus x sub 2 plus x sub 3 equals 0. X sub 1 plus k prime x sub 2 plus k double prime x sub 3 equals 0. X sub 1 plus L prime x sub 2 plus L double prime x sub 3 equals 0. The condition for ABC to be perspective with A prime, B prime, C prime is that the points of intersection of corresponding sides be collinear, i.e., equation 1, the 3 by 3 determinant read by a column, 0, negative K double prime, negative L prime, 1, 0, 1, negative 1, 1, 0, equals K double prime minus L prime equals 0. In like manner, the condition for BCA to be perspective with A prime, B prime, C prime is equations 2, a 3 by 3 determinant read by columns, 0, negative 1, negative K prime, negative L double prime, 0, 1, L prime, 1, 0, equal to K prime, L double prime minus L prime equals 0. From these two conditions follows 3 by 3 determinant, 0, negative L double prime, 1, negative K double prime, 0, negative 1, K prime, 1, 0, equal to K prime, L double prime minus K double prime equals 0, which is the condition for CAB perspective with A prime, B prime, C prime. Hence, if two triangles are in the relations ABC perspective with A prime, B prime, C prime, and BCA perspective with A prime, B prime, C prime, they are also in the relation CAB projective with A prime, B prime, C prime. Two triangles in this relation are said to be triply perspective, chiefly exercise 2, page 100. The domain of rationality defined by the data of our problem is clearly k equal 1 in square brackets. Since the numbers in this domain may be found which satisfy equations 1 and 2, the problems of constructing two triply perspective triangles is linear. The condition for ACB perspective with A prime, B prime, C prime is equation 3, L prime minus L double prime equal to 0. If relations 1, 2, and 3 are satisfied, the triangle will be perspective from four centers. Let K be the common value of K prime and L double prime, equation 3, and let L be the common value of L prime and K double prime, equation 1. Relation 2 then gives the condition K squared minus L equal to 0. The relations K prime equal L double prime equal K, L prime equal K double prime equal K squared, then define two quadruply perspective triangles. The problem of constructing two such triangles is therefore still linear. If we now add the condition for CBA perspective with A prime, B prime, C prime, the two triangles will, by what precedes, be perspective from 6 different centers. The latter condition is, equation 4, K double prime L prime minus L double prime equals 0. With the preceding conditions, 1, 2, 3, and the notation adopted above, this leads to the condition K cubed equal L cubed equal 1. The equation K cubed minus 1 equals 0 is, however, reducible in K. Indeed, it is equivalent to K minus 1 equals 0, K squared plus K plus 1 equals 0. The first of these equations leads to the condition that A prime, B prime, C prime are collinear, and does not therefore give a solution to the problem. The problem of constructing two triangles that are sextuply perspective is, therefore, of the second degree. The equation K squared plus K plus 1 equals 0 has two roots W squared, proper or improper, and in general distinct. Footnote: they can coincide only if the number system is such that 1 plus 1 plus 1 equals 0, for instance in a finite space involving the modulus 3. Hence, our problem has two solutions. One of these consists of the triangles x sub 1 equals 0, x sub 2 equals 0, x sub 3 equals 0, x sub 1 plus x sub 2 plus x sub 3 equals 0, x sub 1 plus w x sub 2 plus w squared x sub 3 equals 0, x sub 1 plus w squared x sub 2 plus w x sub 3 equals 0. Two of the sides of the second triangle may be improper. The points of intersection of the sides of one of these triangles with the sides of the other are the following 9 points. Equations 5. 0, negative 1, 1. Negative 1, 0, 1. Negative 1, 1, 0. 0, w squared, negative w. Negative w squared, 0, 1. W, negative 1, 0. 0, w, negative w squared. Negative w, 0, 1. W squared, negative 1, 0. Footnote: it may be noted that in the ordinary real geometry, two sides of the second triangle are necessarily improper, so that in this geometry our problem has no real solution. They form a configuration, 9, 3, 4, 12, which contains 4 configurations, 9, 3, 3, 9, of the kind studied in section 36, chapter 4. All triples of points in the same row or column or terms of the determinate expansion of their matrix are collinear. If one line is omitted from a finite plane, in the sense of section 72, chapter 7, having 4 points on each line, the remaining 9 points and 12 lines are isomorphic with this configuration. Footnote: they all lie on any cubic curve of the form x sub 1 cubed plus x sub 2 cubed plus x sub 3 cubed plus 3 lambda x sub 1 x sub 2 x sub 3 equals 0 for any value of lambda, and are, in fact, the points of inflection of the cubic. This configuration forms the point of departure for a variety of investigations leading into many different branches of mathematics. Exercises. The problems in a real plane given below that are of the second degree are to be solved by linear constructions with the assumption that the points of intersection of any line in the plane with a given fixed conic in the plane are known, i.e., with a straight edge and a given circle in the plane. 1. Construct the points of intersection of a given line with a conic determined by 1. 4 points and a tangent through one of them. 2. 3 points and the tangents through 2 of them. 3. 5 tangents. 2. Construct the conjugate pair common to 2 involutions on a line. 3. Given a conic determined by 5 points, construct a triangle inscribed in this conic whose sides pass through 3 given points in the plane. 4. Given a triangle A2, B2, C2 inscribed in a triangle A1, B1, C1, in how many ways can a triangle A3, B3, C3 be inscribed in A2, B2, C2 and circumscribed to A1, B1, C1? Show that in one case, in which one vertex of A3, B3, C3 may be chosen arbitrarily, the problem is linear, chiefly section 36, chapter 4, and that in another case the problem is quadratic. Show that this problem gives all configurations of the symbol 9339. Give the constructions for all cases, chiefly S. Cantor. 5. If opposite vertices of a simple plane hexagon P1, P2, P3, P4, P5, P6 are on 3 concurrent lines, and the lines P1, P2, P3, P4, P5, P6 are concurrent, then the lines P2, P3, P4, P5, P6, P1 are also concurrent, and the figure thus formed is a configuration of Pappus. 6. Show how to construct a simple endpoint inscribed in a simple endpoint and circumscribed to another given simple endpoint. 7. Show how to inscribe in a given conic a simple endpoint whose sides pass respectively through n given points. 8. Construct a conic through 4 points and a tangent to a line not meeting any of the 4 points. 9. Construct a conic through 3 points and tangent to 2 lines not meeting any of the points. 10. construct a conic through 4 given points and meeting a given line in 2 points harmonic with 2 given points on the line. 11. If A is a given point of a conic and x, y are 2 variable points of the conic such that ax, ay always pass through a conjugate pair of a given involution on a line L, the line xy will always pass through a fixed point B. The line AB and the tangent to the conic at A pass through a conjugate pair of the given involution. 12. Given a collineation in a plane and a line which does not contain a fixed point of the collineation, show that there is one and only one point on the line which is transformed by the collineation into another point on the line. 13. Given 4 skew lines, show that there are, in general, 2 lines which meet each of the given 4 lines, and that if there are 3 such lines, there is one through every point on one of the lines. 14. Given a plane, 2 systems of 5 points, A1, A2, A3, A4, A5, and B1, B2, B3, B4, B5, given also a point x in the plane, determine a point y such that we have x with A1, A2, A3, A4, A5 projective with y of B1, B2, B3, B4, B5. In general, there is one and only one such point y. Under what condition is there more than one? R. Sturm, Mathematische Annalen, Volume 1, 1869, page 533. Footnote. This is a special case of the so-called problem of projectivity. For references and a systematic treatment, see Sturm, Die Lehre von den geometrischen Verwandtschaften, Volume 1, page 348.
Projective Geometry, Volume 1. This book was written by Oswald Veblen and John Wesley Young. It was published by Blaisdell Publishing Company, London, 1910, and is now in the public domain. It is read by Jim Renholt, with programming and illustration by Jim Renholt, 2019. Thank you for listening.